All right, so we're going to talk about pulsating variable stars because they're so important in our understanding the scale of the universe. They're interesting in their own right. In particular, very important class of pulsating variables of variable stars is delta, the Cepheids, and they're named after their prototype, Delta Cephei. Delta meaning that it's the fourth brightest star in the constellation, or at least it should mean that. I'm not sure if it's true, but constellation name. The brighter stars are given designations which are supposed to be the brightest star in the constellation is Alpha, and then the Latin genitive of the constellation's name. So Alpha Leonis is the brightest star in the constellation Leo, for example. So Alpha, Beta, Gamma, Delta. So Delta Cephei should be the fourth brightest star in the constellation Cepheus. So just for context, there it is. And you can actually watch its variations with the naked eye. It's a naked eye visible star. And so if you go out from night to night and compare its brightness to these two stars right there, for example, you can actually see that it's changing in brightness from night to night. And here is a plot. It's actually quite significant. It changes in brightness by almost a whole magnitude, which is quite noticeable. 4.5 magnitude would be kind of hard to see, and even at Perkins Observatory that's starting to be hard to see because of the light pollution. 3.5 would not be particularly hard to see. It's not super easy, but it's not super bright, but it's definitely readily visible. And you can see it this bright too if you know where to look. They cheated because you can see that they just folded the light curve. Those are the same observations there. As far as I know, these are actual observations, but they did fold them together. There's its brightness versus time, and clearly from a single cycle you could not get that kind of precision in the period. But on the other hand, if you have many, many periods and you apply techniques like we learned in observational astronomy, right? With Coranzo, for example, could come up with the period with all those different techniques it has. Its period is 5.36634 days. So it regularly goes up and down in brightness. And in fact, it's doing so not because there's anything like eclipsing it or anything like that. It's because it's unstable to pulsations. It literally gets bigger and smaller and bigger and smaller, and its surface temperature varies as well. Here are plots of, again, apparent magnitude, like we saw before. And this is radial velocity. So in other words, you look at its spectral lines measured with the Doppler shifts, and when the surface is moving outwards, you see blue-shifted spectral lines, and when the surface is moving inwards, you see red-shifted spectral lines. And so this is the radial velocity in kilometers per second, so it's moving pretty quickly. What am I trying to say here? The plus means redshifted, and minus means blue-shifted is the convention. So here the surface is moving outwards, here the surface is moving inwards. This is the horizontal line is when it's not moving. And then this is diameter as a function of time. So essentially, if you integrate the velocity, you get the position. So you can infer the diameter curve by integrating the radial velocity curve, or you could arbitrarily set the minimum radius equal to 1, and then you can see it gets about 15% bigger at maximum size than at minimum size. And then you can also find the temperature of the surface as a function of time, say from Wien's law. And you see it varies like that. And so let's talk about that. Let's write some things on the board here. So delta Cephei. I never know if it's Cephei or Cephei. You look up pronunciation guides online, and one says one thing and the other one says the other. So there's no tell. Is the prototype, the first one discovered of the so-called classical Cepheids, because as we'll see, there's actually, it turns out, and this wasn't recognized for a while, two kinds of Cepheid variables, namely ones that have metallicities comparable to the sun and ones that have much lower metallicities. And where they live is different. They live in different parts of the galaxy. And we're building up to talking about galaxies, so we'll talk more about the difference between the disk and the halo of the galaxy. And if you look at the radial velocity curve and the apparent and the brightness curve, the apparent magnitude curve, notice they're almost just flipped over versions of one another, where if you flip it around that horizontal axis, the two curves will look very similar. So the light curve is almost, I'll put it in parentheses, a mirror image of the radial velocity curve. But I don't mean like literally I hold it up to a mirror and, have it like, the printing is backwards kind of mirror image. What I'm talking about is reflecting around the horizontal center line. The reflection is around the horizontal center line. So maximum light corresponds to when the surface is moving outwards fastest and vice versa. And minimum light so when it is moving inwards fastest. So we can basically see that on the plots here. It matches up pretty well that when it is brightest is when the radial velocity is most negative, and negative means blue shifted. So when the surface is approaching us the fastest is when the star is brightest, and when the surface is moving away from us the fastest is when the star is dimmest.
So by the surface moving outwards fastest, it means out relative to the center.
Yeah, right. Which would also, out relative to the center, which would also, in other words, when the star is expanding most rapidly. Yeah, when the surface of the star is expanding most rapidly is when the star is at its brightest. But then that won't be when it's at its maximum radius, because if it's expanding, it's still heading towards its maximum radius, right? So that's the next sentence. This means that maximum light occurs a bit after minimum radius, because if it's expanding outwards, it's expanding from when it was minimum size. And we call that the phase lag. Now, you might say, well, why would you expect it to be bright when it's at minimum radius? Well, notice what the temperature is doing. It's hotter when it's smaller. And remember that brightness goes like r squared sigma, 4 pi r squared sigma t to the fourth. So the temperature dependence is stronger than the radius dependence for brightness. So in other words, that it's hotter when it's smaller ends up overwhelming the fact that it's smaller. So it's not brightest when it's largest. It's brightest closer to when it's smallest, actually, because it's also hottest then. occurs a bit after minimum radius. Which we call the phase lag.
I'm going to back out here so that I can now start writing on the other part of the board here.
What questions do you have? Alrighty, so since maximum light occurs near minimum radius and vice versa, in general terms, the star is hotter when smaller and cooler when larger. Since max light occurs near min radius, I'm too lazy to write imam right now. And vice versa. In general terms, the star is hotter when smaller and cooler when larger. Hotter, bluer when smaller, cooler, redder than when larger. And in yet another example of a fundamental discovery in astronomy that was made by a woman. And the good thing about our sciences, even though women weren't given kind of full status early on, they made all these fundamental discoveries, which they're now properly credited for. Henrietta Swan Leavitt. I love this name. What a great name. Henrietta Swan Leavitt. And jump cannon. They knew how to do middle. I'm telling you. Henrietta Swan Leavitt. She lived from 1868 to 1921. Examined some 2,400 classical Cepheids in the Small Magellanic Cloud. Small Magellanic Cloud is a dwarf satellite galaxy of our own Milky Way. It's called the Small Magellanic Cloud because there's also a Large Magellanic Cloud, and their existence was made known to the West by Magellan on his round-the-world voyage. You can only see them if you're far enough south, and you got far enough south to see them. A dwarf satellite galaxy of the Milky Way. So then we'll also put in parentheses, well, that means all these Cepheids were essentially the same distance from Earth because the size of the SMC is small compared to its distance from Earth. So essentially, all the stars are at the same distance. She discovered something really important, namely that there's a relationship between the period of a Cepheid and its average luminosity. So she examines some 2,400 classical Cepheids in a small imaginary cloud, parentheses, and showed that they obey a period luminosity relation. And if they didn't, we would not be able to really know how far away other galaxies are, because these are the stars that were key to measuring the distances to other galaxies besides the Milky Way. In fact, they were the key to the discovery that galaxies really are separate from the Milky Way. The Milky Way is one of just many galaxies. So here is a plot, a boundary plot of the period luminosity relation. Notice that it mentions type 1 and type 2 Cepheids, and that gets back to this idea that it turns out that there are two types of Cepheid variables. And when that was realized, as we will see, our understanding of the size of the universe essentially doubled, because we'll tell the story of how Edwin Hubble discovered Cepheids in the Andromeda Galaxy and used them to determine the distance to the Andromeda Galaxy. And then later it was realized in 1948 that he was assuming they were one kind of Cepheid, when in fact they were another kind of Cepheid. And that meant that the galaxy was actually twice as far away as we thought, as was every other galaxy. So all of a sudden the size of the universe doubled, which solved the mystery, which was, how come the Milky Way is the largest galaxy in the universe as far as we can tell? Answer, the other galaxies are further away than we thought, and so they're also twice as big as we thought. So anyway, here's the modern result for the period luminosity relation. The base 10 logarithm of the average luminosity, angle brackets, the average luminosity, because they're varying in luminosity, right? And so you either have to use the maximum luminosity or the average luminosity, like that. The average luminosity divided by the luminosity of the sun is 1.15 times the base 10 logarithm of the period in days plus 2.47. Or we could also use the absolute visual magnitude, right? Remember, absolute magnitude is another way to specify luminosities implicitly. The absolute magnitude is the apparent magnitude a star would have if it were at a standard distance of how many parsecs? Do you remember? 10. Yeah, 10 parsecs, right? The V here stands for the V filter, the V photometric filter. So the absolute visual magnitude average for the star is minus 2.80 times the logarithm of the period in days minus 1.43. So two ways of expressing the same relationship between period and brightness. So notice that the longer the period, higher the luminosity. The longer the period, the smaller the absolute magnitude, but remember, smaller magnitudes means brighter. So it makes sense that it's got a minus for that relationship.
This is 2.80, correct?
That's a 2.80, not 280. Minus 280 magnitude would be, oh my god, boy, those would be bright. They'd be way brighter than the sun in the sky, even at the distances they're at. So no, that would not be the definition, that decimal point there. But again, notice that there's type 1 Cepheids, which are higher up on the plot, type 2 Cepheids that are lower down, and in fact, for a given period, a type 1 Cepheid has right about 4 times the luminosity of a type 2 Cepheid having the same period typically. There's some spread in that, but as a class, for a given period, type 1s are about 4 times brighter than type 2s, which is why the size of the universe doubled. In other words, Hubble thought that he was looking at, I always have to think about what order makes sense here. He thought that he was looking at, he was using the calibration for type 2 Cepheids and actually observing type 1 Cepheids in the Andromeda Galaxy. So in other words, the stars were actually brighter than he thought they were. They were about 4 times brighter than he thought they actually were. So in order to account for how bright they appear from Earth, if they're 4 times brighter than they thought, you have to move them twice as far away, given the inverse square law, to compensate for that. So every galaxy became, in our heads, twice as far away as we thought it was before it was discovered that there were actually 2 types of Cepheids. And so let's get that into the notes here, that there's this difference between the 2 types. Population Roman numeral 1 Cepheids. Called classical or type 1 Cepheids. So this is another name for them. It's population 1. And as we'll see, in our galaxy we talk about population 1 stars, which are in the disk of the Milky Way galaxy. So the sun is a population 1 star born in the disk. And population 2 stars, which are in the so-called halo of our galaxy. The disk stars are younger in general terms than the halo stars are. The halo stars form first. Globular clusters are in our galaxy's halo. They are older, and therefore they are lower in metals, because remember that the first generation of stars would have been essentially pure hydrogen and helium, because the Big Bang essentially made only hydrogen and helium. But then stars build other elements in their cores, and when they blow up, they return those to the interstellar medium. So later generations of stars had more and more heavy elements in them, metals, as time went on. So older populations of stars tend to have lower metallicities than younger populations of stars do. And in particular, the population 1 disk stars in our galaxy therefore have higher metallicities in general than the population 2 stars. And that's the difference between the type 1 and type 2 Cepheids. The type 1 Cepheids are in the disk and have higher metallicities. The type 2 Cepheids are in the halo and have lower metallicities. And remember that we talked about there's luminosity class 6, which are low metallicity main sequence stars, which means that their atmospheres are more transparent. They don't have as many free electrons in them released by metals, so you can see the deeper, hotter layers, and that shifts where they are on the HR diagram. We've got a similar thing going here. The different metallicities mean different opacities, means for a given period of the star, you see a different luminosity because of the physics of how the pulsations works, which is what we're going to talk about shortly. So population 1 Cepheids, called classical, or type 1 Cepheids. have a different period luminosity relation than population 2 Cepheids. Population 2 Cepheids are called type 2 Cepheids, but there's also another name for them. They're also called W Virginis stars. And that's because the prototype is the star W Virginis. And as we mentioned, a type 1 Cepheid has about 4 times the luminosity of a type 2 with the same period. So when Henrietta Swan Leavitt first observed the Cepheids in the Small Magellanic Cloud, she could see that there was a period luminosity relation because the stars were all at the same distance, but she only knew their apparent magnitudes. Without knowing the distance to the Magellanic Cloud, the Small Magellanic Cloud, she couldn't know what their absolute magnitudes were. So in other words, she wasn't able to come up with, from her data, whoops, I'm writing stuff over there, and the camera's still pointing over here. Let's see, I think I'll just move it over there. She wasn't able to tell from her data what the calibration of the period luminosity was. And originally, the way that it was calibrated was using statistical methods because no Cepheids were close enough to use parallax in order to find their distance. And so originally the calibration had to be done using statistical methods of looking at large groups of them. Now, with satellites, we're able to measure Cepheids parallax, some Cepheids parallaxes directly. So we've got a better handle than was the case back when the period luminosity relationship was discovered. What questions do you have? Yes?
Why are pulsars considered Cepheids? Again, is it
So not all pulsating variables are Cepheids. All Cepheids are pulsating variables, but not all pulsating variables are Cepheids. They are one type of pulsating variable star, a very important type of pulsating variable star. But there are also Miras, which our program Mira is named after. Those are so-called long period variables, the Miras. So
where does the name come from?
which one?
Cepheids.
Cepheids, because the prototype is in the constellation Cepheus. So it comes from the fact that the first one discovered was the star Delta Cephei.
Okay.
So they're called Cepheids because their prototype is in the constellation Cepheus. So for whatever reason, we don't call these Virginids. They're just W Virginis stars. But the same logic would make these Virginids, but nobody calls them that. These, consistency would be we would call these Delta Cephei stars, but we don't. They're just called Cepheids because whatever, how these things go. Because astronomy, that's right. Shut up and just accept it. Just shut up and calculate. Yeah, just historical accident, essentially. So this is showing the distinction between the population 1 and population 2 stars. You can tell spectroscopically. Here on the top is a population 2-star spectrum, here's a population 1-star spectrum for the same spectral type. And what you can see is that the metal lines, not the hydrogen lines are of comparable strength, but the metal lines are stronger in the population 1-star. And we had said, we made a big deal about the fact that the main difference in strengths of spectral lines comes from the temperature, not from the abundances of the elements. But that's not completely true. The abundances do matter. Stars with higher metallicities do have stronger lines of metals, just because there are more of the atoms there to absorb photons. And so here you can see that the metal lines are stronger in pop 1 stars than they are in pop 2 stars. And yes, people get tired of saying pop emission, so you hear pop 1 and pop 2 all the time. People talk about that.
Soda 1 and soda 2.
Yeah, soda 1 and soda 2. Yeah. Here in the Midwest, in New York City, they call them soda 1 and soda 2 stars. Yes. They're so dumb out there. Right, lovely one. So, what did I say here? Here we have the stars on the HR diagram. And what we can see is that the Cepheid variables lie along an almost vertical line in the HR diagram. And this is called the instability strip, because stars along this strip in the HR diagram are unstable, not as in they're going to blow up, but in other words, with the sun we know that it keeps over very long time scales, essentially a rock, who did that? A rock solid radius, surface temperature, luminosity. We will momentarily discuss. Suppose I gave the sun a squeeze. We'll see that, well, it would expand back out again, and it would ring a little bit. If you could somehow magically squeeze the entire sun, it would oscillate, but the oscillations would be damped, and then it would go back to being nice rock solid radius, luminosity, temperature. The deal with pulsating variable stars is that instead of that rock solid stability, they actually are heat engines. They actually pulsate in and out because there's no fixed luminosity, surface temperature, and radius that works for them, so to speak. And so sometimes pressure is a little stronger than gravity in the star's outer layers, and it expands. But then it reaches a maximum expansion radius, and at that point, it flips around, and gravity is stronger than pressure, and it contracts. And so it goes back and forth between there being a net outward force on the outer layers and a net inwards force on the outer layers. And so it pulsates instead of having a nice rock solid, steady radius, luminosity, surface temperature. Stars on the HR diagram, stars that are in the instability strip on the HR diagram are in that situation where they pulsate, is what it comes down to. So it's called the instability strip because they do not have a stable radius and surface temperature and luminosity. They vary. Question?
So this happens to, quote unquote, all stars that pass through this strip?
Yes, any star that passes through that strip will become a Cepheid variable. Notice too, there are so-called RR Lively variables at the base of the instability strip. And then there's the Miras, the long period variables over here in a sort of other instability strip, although this is the one that gets the name of the instability strip, the one that has the Cepheids in it. Okay? So, qualitatively, here's why there's a period luminosity relation. Consider two bells, big Liberty Bell and little Tinkle Bell. And I smack them. They oscillate. Which one rings at a higher frequency? The big bell, the little bell. Even vocally indicating. The little bell rings at a higher frequency. You can think of these stars as bells. They're ringing, if you will. Their surfaces are vibrating. And just like a big, massive bell rings at a lower frequency than a small, less massive bell, so too, massive stars ring at a lower frequency than less massive stars do. What puts stars in the instability strip? They are high mass stars that after leaving the main sequence, remember when massive stars leave the main sequence, their evolutionary track wanders back and forth along the top of the HR diagram. And so what happens is, sometimes the evolution of the star after it leaves the main sequence carries it into the instability strip. A given star, like this 5 solar mass star, a given star can, in principle, go through the instability strip multiple times. So a 5 solar mass star sometimes is a Cepheid variable, sometimes it is not. Same deal for this 9 solar mass star here. And the more massive the star, the higher up it is on the HR diagram, the higher its luminosity is, and the more slowly it rings. So the reason there's a period luminosity relation is that more massive stars ring at lower frequencies and have higher luminosities. So that's really what it comes down to. That's qualitatively you can understand that it makes sense that there's a period luminosity relation because the brighter Cepheids are higher mass post-main sequence stars than the dimmer ones are, and the higher mass makes them harder to shake. And so they ring at lower frequencies, if you will, than the lower mass ones do. Okay? Any questions about that? What questions do you have? Okay? So, let's talk about the physics of stellar pulsation. You might go, I don't know, just write what I just said in your own words about, why there's a period of luminosity relation, right? In other words, I passed out the pictures, and you should say somewhere more luminous Cepheids are higher mass post-main sequence stars, and just like a bigger bell rings slower than a smaller bell, a more massive star rings, vibrates at a lower frequency than a less massive star does. Let's see, so how late did we start? Because I kind of want to get a restart time in for the day here. So I think my fault, but whatever, suffer. How about if question number 1 is, should we put in a third hour today, or does that not work for people?
I think I have plans, but
You think you have plans? Yes.
let me see if I can move those back.
Cancel those plans. We don't have to cancel those plans. We can put it in some other. How about you?
I don't care.
You don't care. Yeah. You don't care.
I have to stay here because I got work at 6:30,
Oh yeah.
so I'm ready to do it.
Yeah. Okay. Well, let me start writing about the physics of stellar pulsation. And let me be sure that thing is pointed in the right direction for all of this.
These like a remote for the camera. Yes. The physics of stellar pulsation.
Let's imagine compressing a star to smaller than its equilibrium radius. Probably not as much as I've indicated there, but in other words, imagine that you could squeeze the sun down to a smaller radius. What would happen? Imagine compressing a star to smaller than its equilibrium radius. You'll heat up the interior of the star because you'll be doing PV work on it. If I take a gas and I compress it, then I am doing work against the pressure that it's pushing back on me with. And so I do PV work on it, just like if I compress gas inside a cylinder, it heats the gas inside the cylinder. The compression will heat the star, do the PV work. And drive up the pressure so that it exceeds gravity. This has to be true. In other words, you could say, yeah, but you also made it more compact, so gravity is also increasing. But if the star is stable, it has to be that the pressure would increase more than the gravity here, because otherwise, if the gravity would increase more than the pressure, then any random decrease in the star's radius would keep going because the gravity had become stronger than the pressure. So the fact that there's an equilibrium radius in the first place means that if I squashed it, the pressure rise would be more important than the increase in gravity. Pressure has to become stronger than gravity here. So the compression will heat the star and drive up the pressure so that it exceeds gravity. So what's the star going to do? If I let go, I squeeze it, I let go, pressure stronger than gravity, what's it do? It starts expanding. This pressure is stronger than gravity, pressure is outwards, gravity is inwards, the star will expand. And so the star will expand. So it's expanding. Once it's back at its equilibrium radius again, once it's been expanding, so it's still moving when it's back at its equilibrium radius. So it keeps going. It overshoots. It expands past the equilibrium radius. But again, the star is stable in the first place, so now what must be happening is the pressure is falling, and now its gravity is going to be stronger than pressure. Because if I had expanded the star, I know that both the gravity and the pressure would become weaker, but it has to be that in that case, the pressure drop-off would be faster than the gravity drop-off, because for the star to be stable in the first place, if I expanded it, it would have to want to return to its equilibrium radius. So in other words, the star expands past its equilibrium radius, and now gravity is stronger than pressure. And so what's the star do? Well, it doesn't immediately start to contract, but if gravity is stronger than pressure, that means the expansion begins to slow down and eventually stop and reverse itself, and it starts to fall back in again. In other words, the star is going to oscillate. Just like a simple harmonic oscillator, mass on the spring. It overshoots the equilibrium. There's no force, but it's still moving, so it overshoots the equilibrium. And then the spring starts pulling back, and the mass slows down, stops, reverses, comes through the equilibrium again. No force, but it's moving, so it overshoots it again. So it oscillates like a spring on a mass does. So if you were to squeeze the sun and let go, it would oscillate. But not forever. These must be damped oscillations because otherwise the sun would be oscillating now. Or at least, well, the sun is oscillating, but not with high amplitude. There's sound waves traveling through it, helioseismology, we're not going to get into all that here. But as we'll see, the sun would execute damped oscillations, actually. The amplitude would decay. And so the star would go back to being in a stable equilibrium after a few cycles of oscillation. So, the star will expand. Let's complete the story here. It will still be moving when it is back at its equilibrium radius. So it's going to keep going. So we'll overshoot the equilibrium like a mass on a spring. When past its equilibrium radius, the temperature and pressure fall below their equilibrium values. Gravity exceeds pressure, so eventually the expansion halts, reverses, and overshoots the equilibrium again. Thus, the star will oscillate. That's what I'm about to write, but I like to say it first. When past its equilibrium radius, the temperature and pressure fall below their equilibrium values. Gravity exceeds pressure. Level on the board here. So eventually the expansion halts. Reverses and overshoots the equilibrium again. And thus the star will oscillate. Our star will ring. What questions do you have? Yes.
So for the Cepheids, maybe I misheard you, but did you say that they don't have an equilibrium radius?
They don't. So what we're going to get at is that for a star like the sun, if you plotted radius versus time for something like this, you would see damped oscillations. So it just goes back to equilibrium and stays there. For Cepheid variables, if you squeeze a Cepheid, so it would have kind of a nominal equilibrium radius, but any perturbation starts to grow. So in other words, the idea, squeeze a Cepheid and the oscillations grow instead of damping. Now, there there will be damping and you reach an equilibrium amplitude of oscillations where there is as much loss due to damping in every oscillation as there is input due to driving. And we'll talk about how they're driven. But in other words, with Cepheids, what would happen is if you gave it a low amplitude of oscillation, then every cycle more energy would go into the oscillations than was being damped out of the oscillations. So they actually start to grow in amplitude until they reach this equilibrium amplitude of the oscillations where they're losing as much energy per cycle as is being put in. And so that's what they do, is they come to an equilibrium oscillation amplitude instead of an equilibrium radius, is what it comes down to. And in principle, you could get the thing to have an equilibrium radius where it didn't do anything, but it would be unstable like me trying to balance this. In other words, any little perturbation will start to grow. In that case, it's an unstable equilibrium is what it comes down to, unlike for the sun where it's a stable equilibrium. Good question. Okay, it's break time. How long is our break? As in, is it 10 minutes or is it days?
Don't know.
You don't know.
Reply.
What's that?
We can do it, we'll just go, however long.
Well, I don't want you to get in trouble with anybody.
It's just a